Going on 112 when we're done. We have talked about some transformations already. Reflections, translations, rotations. Then we looked at symmetry and how it all played into symmetry. Then we looked at how all that worked on the coordinate plane. So today we're going to talk about dilations, which again, like the rest of it, is not brand new to you. But we are going to look at some of it in a little bit of a different way than what you've seen before. So the first blank is the definition of a dilation. So a dilation is a transformation that changes the size of a figure, but not the shape. Okay, and we talked about that the other day when we talked about these. So that means that a dilation is a similarity transformation. The other ones we've talked about so far have all been congruence transformations. A dilation is a similarity transformation, which means that it is not a what? What's that word that starts with an I? Isometry. Okay, so a dilation does not fit into the category of isometry because we changed the size. So it is a similarity transformation in which the lines connecting every point P with its image P prime all intersect at point C. So here's what that means. If I have this line segment PQ right here, and I'm going to dilate it, and it becomes P prime Q prime, right? Then C is what's called my center of dilation. And it says the lines connecting every point with its image all intersect at C. So if I connect P prime to P and Q prime to Q, do you see how they intersect right there? And if this was a triangle and at a third point, when I connect those two, that end up there right there as well. And that point C is called the center of dilation. And then it goes on to say, and CP prime over CP is the same for every point P. So what that means is that the distance from C to P prime, whatever that length is, over the length from C to P, so this number over this number, has to be the same for every single point. So that means the length of CQ prime over CQ has to be the same ratio, has to be the same fraction, because everything's changing by the same rate. And that also creates little similar triangles here in the end. Okay. So then what we have, how we know how much to change it or how much it's been changed by, we have what is called the scale factor. So the scale factor, which is K, it's a lowercase k, of a dilation is the ratio. Mathematically, that word should make you think of what? Fraction. Of a linear measurement of the image to a corresponding measurement of the preimage. So that means like lengths of corresponding sides if we're talking polygons. So then in the figure, and there's something you have to fix in this little fraction here. In the figure, K, which is your scale factor, is equal to, this should say P prime Q prime, not P Q prime, P prime Q prime. So the length of the red segment over the length of the blue segment. And that would give you your scale factor. Okay, and again, if it was a polygon, you'd have corresponding sides. So we're going to actually construct this. Now the thing that is a little bit different than what you have most likely seen with dilations before is that it does not just change the size, but when you're constructing them, whether it's on a coordinate plane or not, then you are also changing the location of it, all right? And I forgot to mention at the beginning, one thing that is done with dilations a lot, which you may have done in the past or at least seen done in a math class or even in an art class in a lower grade, is if you take a picture that maybe you got out of a magazine or you printed off the internet or whatever, and you mark off a grid on the picture, and you take a piece of poster board and you mark the grid off on the poster board as well, and then you transfer the picture square by square. Y'all ever seen anything like that done? Okay. And so if you're doing that for a math class, that's a lower grade dilation project a lot. If you're doing that, you're talking about dilations. If you're doing it in art, then you're talking about scale drawings, but really it's the same thing either way. Okay, so the idea of just everything changes at the same rate. All right, so we're going to construct this. So you need a ruler, right? You need a ruler, not just your ID badge, not just a straight edge, a ruler, which there's plenty of them around, and colored pencil maybe if you want. You don't have to, but that can be helpful. All right, so right here, we have this point, which is point P. And then you're going to label this triangle A, B, C. Okay. Then with your ruler, which really is just going to work as a straight edge right now because we're not measuring anything yet, you're going to draw it, you're going to connect some things. But this point P that I gave you is like a ginormous point. And if you measure from the outside of the point, it's going to be different than if you measure from the inside because I made it way too big. So you have to make sure when you're drawing that you're not drawing from like the edge of the point. Like try and hit it dead center every single time. It makes sense. You got to aim for the center and it'll be fine. So you're going to draw a ray, basically, from the center of the ginormous point I gave you through each vertex. So make sure you extend it through. Don't just like connect them. I'm going to do that for each of the 3 points. Oops, might skip. Okay, so then what we're doing here, it says that we're going to dilate the figure by a scale factor of 2. Okay, so what that has meant to you in the past is that basically each side length gets doubled, right? But that's not how we're constructing it. You are not going to measure the side length of the triangle and then go try and draw it twice as big, because that's not going to give you the precise location of where it ends up. What the definition above says is that the distance between the points is what's actually changing. So you're going to use your ruler. Let me grab my ruler. And I would highly suggest that you use centimeters and not inches. It just makes it a whole lot easier. You're going to measure the length of the line segment AP. So I'm going to measure the distance between A and P. And remember, try and hit the center of the ginormous point I gave you when you're measuring. Or is it throws your measurements off? And then my distance which would be different than yours, obviously. But on my ruler, I get 23. You probably have 2 point something. It may not be 2.3, but it's 2 point something. Or one something. Is that what it is? Okay, I'm sorry. So whatever it is, but you don't have it like it's not in the 20s. It's like a 1 point something. So now I could move my ruler and then measure the same on the other side, but you can also just leave it. Take whatever the distance is between A and P and multiply it by 2 in your head and then find that length on your ruler. So for me, I'm at 23, which means I would go to 46 and mark my point. And then there's my point that is now going to become A prime. And then you do the same thing from P to B. Okay. Whatever your distance is, then you double it. Okay. So. Yes, you can. This becomes B prime, and then from P to C. Okay. And then get rid of my ruler. Okay, so then you use a straight edge and you connect the points, and your figures should look similar to each other, right? And then use your ruler to do some actual measurements. After you've done all of that and you have a picture that looks similar to this, measure the length of line segment AB, and then measure the length of line segment A prime, B prime, and see if you did double the side lengths without actually doubling the side lengths. Now, and you should get the answer of yes, or at least pretty darn close. If your measurements, weren't perfect, it should be pretty close. Anybody having issues with what to do? Pretty darn close is good. And you can, measure all 3 side lengths if you want, just kind of get the idea. Did I already pick y'all's up? Or you lost yours? Where's yours? No? Okay. Right. Which one? That's fine. Okay. Any questions at this point? Now, did you notice how the pink triangle got pushed away from that center of dilation? If my center of dilation is somewhere else, even if I moved it down here, then my pink triangle would be the exact same size it is, but it would be in a different place. So if I pulled point P back to here, okay, and it was right there, then would that pink triangle be closer to the blue one or farther away? Farther away, because now the distance from P to A is farther, which means from P to A prime is going to be farther, so it would be pushed away even farther. Does that make sense to you? So it has more than just changing the size. It's also about a location change depending on how you're applying it. Okay? So next page. A dilation enlarges or reduces all dimensions proportionally. Okay? Enlarges or reduces all dimensions proportionally. So a dilation factor greater than 1, right? So if my dilation factor is greater than 1, then it is an enlargement or expansion. A dilation factor greater than 0 but less than 1 is a reduction or contraction. So the fact that it says greater, we can choose from either greater than 1 or greater than 0 but less than 1. What is left out of that? Negatives. And what else? Like there's no negative numbers included. What else is left out? Okay, 0 and my negative numbers, and what else? 1. 1 is left out. I can have decimals and fractions because that's how I get between 0 and 1, but 1 is not included in there, right? Because there's no greater than or equal to. So if your scale factor is 1, basically you don't have a size change. Does that make sense to you? Yeah, it's just the same figure. And so you have to have a size change. That's a little bit different than when you talk about congruence and similarity. Congruent figures are similar. They just have a boring, kind of similarity because their scale factor is 1, or their similarity ratio is 1. But for dilations, you can't have a scale factor of 1. Okay, so now we're going to do the same kind of construction here, but and your point P is ginormous again, so make sure you aim for the middle. But this time your scale factor is 1/2, so that's going to be a reduction, right? So think about when you're dilating, and I think we talked about this the other day. When you go to the eye doctor and they dilate your eyes, right? They're making your pupils stay open so they can see into your soul through your eye, right? And so I said that earlier today, and somebody said, but I thought when your pupils dilated, they got smaller. Well, they do, because it's a reduction or an enlargement. They expand and contract. You walk out in the bright sunshine, and your pupils dilate smaller. You walk into a dark room, and they dilate larger. So it's a getting bigger or smaller type of thing. Yeah, it just depends. All right, so with my straight edge, I am going to connect point P through each one of the vertices, like so. And then I need my ruler again. And I'm going to measure the distance from P to A. And so now, since my scale factor is 1/2, when you find that distance, what do? Divide it by 2. So my distance happens to be 100, which means I'm going to make it 50. That's A prime. And then you do that for each one of them. How? Geometry is always fun. Where have you been? I guess not. Straight edge moved. I hate when that happens. Okay, so remember when you're done, your triangles should look similar, and because technically they are, if everything is done exactly perfectly. So if they don't even look like they're the same shape, something went wrong somewhere. And if you're unsure if you did it right or not, that's when you go back and you measure. Measure the length of AB, and then A prime, B prime. Measure AC, and then A prime, C prime, and see what happens. And one thing I didn't label on the other one, which I should have, is when you are doing this, then the length of A prime P is congruent to A prime. Those two pieces are congruent. These two pieces are congruent, because that's what we did. We cut it in half, right? So technically A prime is the midpoint. On the front, we doubled it, so those segments were congruent also. I just didn't label them. Okay. Are we all good? Pretty darn close. That is what we were looking for. Okay, so go ahead and measure some things. I'll give you a second to finish that up. No, it's tea. It took a lot of tea. I don't like water. I know. And I'm so sad the days I forget my cup. I'm like, oh, it's going to be a bad day. Yeah. Yeah. My morning classes hear that a lot. Oh, I didn't have my coffee this morning. Sorry. Yeah. All right. Any questions? Everybody good? Anybody like way off and this isn't working out for you, or it's all pretty darn close? Okay. Yes. Yes, but in a little bit of a different way. But we'll talk about that at the end. All right. So now we're going to look at this next question, which is definitely a question that you could have done a long time ago too. But we're going to go about it a different way than you would most likely go about it if I just let you do it on your own. So it says an artist is creating a large painting from a photograph by dividing the photograph into squares and dilating each square by a scale factor of 4. If the photograph is 20 centimeters by 25 centimeters, what's the perimeter and area of the painting? So this is what I was talking about, like with that activity. So we're going to draw a picture of our photograph. Okay, so here's my photograph, and it is 25 centimeters and 20 centimeters. Now, I don't want they didn't ask me for the perimeter and the area of the photograph. They asked me for the perimeter and the area of the painting. So I could find the dimensions of the painting and do it that way. And there's nothing wrong with that, but we're going to go about it a different way for a reason that I'll talk you through while we do it. So I'm going to find the perimeter and the area of the picture. And so the perimeter could just be 2 times 20 plus 2 times 25. Y'all agree with that? It's not like it's hard to find. What's the perimeter? 90. So I get 90 centimeters for the perimeter of the photograph. Area is equal to base times height, so that's going to be 25 times 20. So the area is 500 centimeters squared. So I wish I had changed the problem where I didn't give you what I gave you, but I could give you a different problem where I don't give you these measurements. Instead of giving you these measurements, I tell you that I have a photograph that has a perimeter of 90 centimeters and an area of 500 centimeters, and I want to know what the perimeter and the area of the painting is going to be. You don't have enough information to find these lengths, so then you can't go and just multiply each one of them by 4 and go find that. You have to go about it a different way. So I could, if I was going to find these dimensions, which I know you probably already know what they are, but it doesn't matter. We're not going to actually even write them down. This would be 4 times 25. This would be 4 times 20. Do we all agree with that? Okay, so what happens here when you're dilating it is that the dimensions all get multiplied by 4, right? The area then would be multiplied by what? 4 squared. And I want you to see that right here. And when I find the area, I'm multiplying the base times the height. So the 20 and the 25 still get multiplied like it did over there. But then the 4 gets multiplied by the 4. That's where the 4 squared comes from. Does that make sense to you? That's why you square it when it's area. And what about perimeter? What would the perimeter be multiplied by? 4. Remember, it always matches the units. The units on the dimensions are centimeters, and so it's also in the perimeter. And area is centimeters squared. So this exponent matches this. Right? So if the dimensions get multiplied by 4, the perimeter gets multiplied by 4. Area does not get multiplied by 4. It gets multiplied by 4 squared. So if you have the perimeter in the area, then to find the perimeter of the painting, it's 90 times what? 4, because the 90 is coming from there. And then that means the perimeter is 360 centimeters. Then to find the area, I use the 500, but it gets multiplied by 4 squared because it's area, so it's 500 times 16. So that is 8,000 centimeters squared. Tell me why you said 4.
Oh, because I was like, so I made the 1,000. Oh, I messed it up.
Oh, no, that's okay. I thought you were going to give me a really profound reason, because I can tell you why that might be easier. If you're thinking like, oh gosh, 500, even 5 times 16 might not pop into some of your heads, but isn't 16 8 times 2? So 5 times 8 is 40, so that would give you 4,000. You multiply by 2, you get 8,000. You see how you can break it up, even when it's not broken up for you? And so I thought that's what you were going to tell me. Oh, dang, I messed it up. You could have saved yourself there, see? It's all fine, though. I mess up all the time. Any questions? Are we good? Okay. So would it have been, quote, easier on this problem just to find the dimensions and do that? Yes. But I'm trying to show you that you may not be given that information and you need to know how to handle it. Okay? Are we good? Awesome. All right, next page. So now we're going to look at them on the coordinate plane. And so we have the dilation, or it says if point P is point at XY, what's wrong with how this is written? P is not capitalized. That should be a capital P since it is a point. So you've got P, which is at XY. It's the preimage of a point. It's the preimage of a point of a dilation centered at the origin. Okay, that is key here. Your dilation could be centered anywhere, but the rules we're coming up with on the coordinate plane today only work for the ones centered at the origin, okay? With the scale factor k, that's your lowercase k, then the image of the point is p prime, which is k times x, k times y. So for instance, here's my origin, here is the point, and then all you do is literally take k and multiply it by each one, so that's what you get. It's that easy. Now remember, when we talked about what the scale factor was, it did not include the negatives and it did not include 1. But you can have a negative k as a scale factor. But technically the k part of it, not the negative part of it, is the dilation. So here's what happens. Here's my preimage, for instance, which is the blue one. I multiply it on a scale factor of k and get the green one. If I have a negative k, it ends up here on the red one. So the red and the green are congruent, but I have multiplied x and y both by a negative, or so it changes the sign on them, and what does that do for you? No, if all I do is change the sign, that's what kind of transformation? No. Negative x, negative y, what does that do? It's a 180-degree rotation, okay? So basically the negative k is 2 transformations at the same time. It's a composition of a rotation of 180 degrees and a dilation with a scale factor of k. So that's what this says.
I thought a dilation could be, I thought it doesn't change size.
No, it changes size. It does not change shape.
So it can't change position.
Oh, yeah. It'll always change position. Yes. So dilation with a scale factor of negative k is equivalent to a composition of a dilation with a scale factor of k that is rotated 180 degrees about the origin. So the positive value of k is what actually does the dilating, and then the negative just tells you it rotates, and it all happens at the same time.
So
yeah, it wouldn't rotate. Right. We good? All right, so let's do this example. It says, What's the what? Where? No, it's just a line that divides. It's not a blank to fill in now. All right, so draw the image of a triangle with these vertices. So let's start by plotting these points. A is at negative 1, 1. B is at negative 2, negative 1. C is at negative 1, negative 2. Yeah, you don't necessarily need the ruler. ID works fine. Oh my gosh, I can't hit the points. Okay, so we have this triangle. And then it tells me that my scale factor is a negative 2. So K is negative 2. My mapping here then is that XY maps to, well, I just take K and I multiply by X and Y, so that'll give me a negative 2X, negative 2Y. No, whoa. That is not what makes it smaller. What we just talked about is that the positive value of this does the dilation. The negative does what? It rotates it. Okay? So when you wrote this negative tells you something before you ever start. Right now we're in quadrants 2 and 3. Because K is negative, what quadrants will I end up in? 1 and 4. Because I'll end up over here, right? Because it's going to rotate 180 degrees. And then the positive value of this, which is 2, is that going to get bigger or smaller? Bigger. So when I'm done, it should rotate around here and be bigger. And if not, then something went wrong somewhere. So then I can get my points. A prime, since I'm multiplying both by negative 2, I'm at negative 1, 1. So this is going to be positive 2, negative 2. B prime, which is currently at negative 2, negative 1, is going to be at positive 4, positive 2. C prime, which is currently at negative 1, negative 2, is going to be at negative 2, I'm sorry, not negative 2. It's going to be at 2, 4. And then we can plot those points. So A prime is at 2, negative 2. B prime is at 4, 2. C prime is at 2, 4. And then I connect them with a straight edge. What do you mean? Oh, no, you don't have to. So his question was, do I have to draw the center of dilation? No. I'm actually going to do that on just one thing here to show you, but no. The center of dilation on the coordinate plane right now will always be the origin, so it's fine. But when I connect the origin to A, right, that's one diagonal through my little squares. And when I connect it to A prime, which I forgot my prime on there. Ah, dang it. Prime, there we go. Then you see how this is one diagonal and this is 2? So A prime is twice as far from the origin as A is, and the same is for B and C. But it's twice as far and got rotated around. Where if it didn't get rotated, if this was a positive 2, then A prime would be right here. Does that make sense to you? It would just still connect like that. Everybody good? Any questions? All right, so you work on the next one while I hand out the homework and check roll. Mm-hmm. Mm-hmm. Exactly, yes. So his question was, if the scale factor is 1/2 and the y value is 0, then it doesn't change. And really, no matter what the scale factor is, if your y value is 0, it's not going to change. Yes, yeah, because all you remember, you literally multiply, and if what you still get is 0, then that's what happens, and it doesn't change. That's a good question. All right, so this is what I got. Do you agree with me? Yes. Okay, so one thing I want you to notice is that when your K value, the positive K value was greater than 1, you see how the image got pushed away from the origin? But when it's less than 1, it gets pulled towards the origin. And because the center of the dilation is the origin, that's why, I know it seems weird, and this is why there was that question that the y value on your R was 0, and now it's still 0, but you feel like everything should be changing. But when it's on an axis and it's being drawn towards the origin, it's just sliding its way down this way, where these have to slide their way in diagonally. Does that make sense? So if it's already on already on an axis, it's going to stay there and just slide towards the origin. Okay? Any questions? Awesome. All right. Then go ahead and get that glued in. Look at your assignment real quick. The front looks very similar to the other transformations ones you had. So the directions on the bottom are the same. Pretty much everything you see here needs to be done on the graph ones. The mapping, the prime notation, both pictures, all that stuff. On the back, number 12 is where you're doing the center of dilation. So you're not having to construct one exactly like what we did on the notes. You're basically doing the opposite. But if you can do what we did on the notes, then you should be able to wrap your mind around what number 12 is asking you to do. So it does require a straight edge from you. It does not require a ruler, okay, because you're not having to actually measure anything. All right, so you have some time, but I don't know how much because I forgot to go look at what time we get out today, but I will go do that here in just a second.